My apologies for everyone viewing the recording later. We skipped two lecture slides. I mean, we discussed them, but without recording. On Euclidean transformations, you can review them on your own later. All the slides are available on GitHub. Okay. So let us finish the discussion here. So how does this magic of multiplication works? Well, we can multiply as usual, matrices as usual. So the first column with the first row. Notice what will happen is this guy will be multiplied this guy, 0 will multiply this guy, and we get what we expect, right? This is the expression for so T2 in the world frame, and there's T2 in T1 frame times T1 in the world frame. So this somehow worked. Now, next we multiply second row with the first column. We get 0 because 0 times T, 1 times 0 is 0. Okay. Good. So as we can see, this 0 persists indeed. That is a good result. That 0 persists through matrix multiplication. All right. Next, we multiply the first row. I apologize for the noise. We have some sort of a car outside. All right. We multiply the first row by the second column. By the second column. Okay. What do we get? Well, we get this expression. It is, notice, T1 in the world frame times R or 1 or 2 in the T1 frame. So this part is clearly a R or 1 or 2 coordinates in the T1 frame being transformed into the world frame. And then we have 1 times R01, that is this guy. So overall here, what we have is the position of the point R02 in the world frame, and that is given by position of the R01 in the world frame plus R0102 in the world frame, what with transpose coordinates transformed. I hope I convinced you that it works. It works in general. It works in general. So let me show you the general setup. In general, what happens is we have frame transformation given like this. We have a next frame expressed in terms of the previous frame by its basis coordinates in the previous frame, by the distance between the previous origin and the current origin expressed in the basis of the previous frame, zeros and 1 here. And to get world coordinates of the frame number n, you multiply all previous frames. We're talking about series linkages, right? About series of frames. We multiply all previous frames like this, and we get the world coordinates of the last frame, or of the frame number n. Does this make sense? Does this make sense?
Yes.
Do we have questions? No questions. Have you seen this idea before?
Maybe not exactly in your notation, but I would say the idea to put both rotation and translation into one matrix, and it will be 4 by 4. Yes.
Oh, so you have seen before. Cool, that's very good. And in which class?
I believe some first notes were in first linear algebra.
Oh, cool. You had a very good linear algebra class. Huh? That is very impressive. Okay. So now you see how frame transformation can be done with 4x4 matrices. Good. That is quite popular. However, this is somehow how should I put it? This use is somehow mostly focused on forward kinematics. And forward kinematics is, of course, a very important part of robotics. But I want to give you just my view on the matter, right? The most, like in practice, what is important is to do forward kinematics correctly. And this includes tasks that you do in one evening. Like someone asks you, what would be the frame transformation from 0 to 0? For some reason, they need help. You can do it in one evening or 10 minutes, depends on how fast you are. And you give them the answer. It's important to give them correct answer. And here your focus is on verifying your answers, not on arriving to them fast. And so I don't know if frame transformation or matrix multiplication or any other method, there are other methods, that is not exhaustive list for sure. If they give you advantage in terms of verification, basically you need to come up with test cases and stuff to verify your answer. All right, so that is one situation. Here, so what I'm trying to say is important to think how you're going to verify the correctness of your answer, not how you arrive there. Okay, another situation is you develop software for a particular robot, and this software uses frame transformations. If you're lucky, you'll get software package which already does frame transformations for you. I believe in ROS there are plenty of software packages that do it. So in this case, you won't have to develop your own frame transformations. And very typically, when you work with URDEVs, packages that read URDEVs also can perform frame transformations. That is very typical. So again, you won't have to do your own frame transformations. What is important in this case is being able to understand how software package interprets those things. For example, when it gives you a frame transformation, what does it imply? Is it the basis of the I frame in terms of the frame I-1, or is it something else? Is it a matrix to which you need to multiply the vector in the world frame to get to a vector in the frame I-1, which would be different, and so on and so forth. So you need to basically be able to understand what's going on. And for that, you read documentation, but you also perform basic tests. You cannot just rely on documentation, because if you perform critical development, as in development on which something depends, you have to test. So don't treat frame transformations as a basic thing that you studied in your childhood and now it is beneath your dignity to test. No, that is a source of errors and treat it as such. Your third-party software may deceive you, so test it. Make sure you understand in which basis each vector is, and so on and so forth. One of the beta tests is to find a graphical picture where if you draw a vector correctly, it would look correct on the screen. If you draw a vector incorrectly with a faulty understanding of bases, it would appear incorrectly on the screen. Moreover, you can perform those image-based tests in motion. If your robot moves, your vectors that you draw should move correctly with the changes of frames. And if you know, but you have to think. You have to think about scenarios for your robot, which would make it obvious that the frames move correctly, and so on and so forth. Okay, all right. So in this case, what I'm trying to say is it is not so important to think about which particular frame transformations you are going to use, like how you're going to multiply and so on. Just think about verifications. Also, performance is important. Here, it is very tempting to say, okay, 4x4 matrix multiplication requires extra operations, like you have you can count how many multiplications and additions you need to do to perform matrix multiplications here. And it should be more than just multiplying matrix by matrix, matrix by vector, as in normal ones, because of those extra zeros and one that we lug around. It is very tempting to say that it is wasteful. However, 4 multiplications by zeros and 1 multiplication by 1, I think is so insignificant in terms of the amount of computations that you can safely ignore these issues. That is not a very big number. Maybe in some critical operations it is, but I don't think that will be a source of waste of computational time. Instead, you have to just in general think about how you compute things. Like, for example, if you do it numerically, that is one thing. If you do it analytically, as in you use symbolic computations, that is a different thing. Often enough, the same computation does not need to be performed. Like often enough, there is a way to compute forward kinematics once somewhere, and maybe in optimized C code, and then pull it somewhere else. So I guess, and if you, for example, do it in NumPy, you lag around classes. If you do it in C, maybe you can avoid lagging around classes, and so on and so forth. So maybe when you do forward kinematics, consider questions of optimization. But also, often enough, you would have to consider use of third-party software, which would be optimized already. So those are things that I want you to keep in your mind. It's good to think about computational optimization. It's good to think which is more convenient, but most importantly, think about issues of software. Think about computational issues. All right. So what time is it? All right. So next we'll consider topic of Jacobians. Topic of Jacobians. All right. Next we'll consider topic of Jacobians. Well, I wanted to split the class with at least 10-minute break as last time to see like if it works or not. So maybe we'll go like 3 more slides, then we'll take a short break. Then there will be like a very difficult section at the end. So I want us to be kind of refreshed before the last section. So let's go through a few easy slides, and then we'll go to the break. Okay. So this lecture so far, and the whole previous lecture, we'll focusing on how to find radius vectors, what we call. So vectors that depict positions of points with respect to something. Or radius vectors in the world frame. So radius vectors that depict position of points with respect to the origin of the world frame. Okay. And we're given position and rotation of frames. So today, let's focus on derivatives of those expressions. So consider vector arc k, which describes position of the point k. What is the derivative of this vector? So in order to answer this question, we need to understand which parameters appear in expression for rk that are changing with time. Because if rk is constant, the derivative is 0. If rk is parameterized as, for example, let me show you. R sub k is equal to, let's say, x, y, z, and x, y, z are all functions of time, then the derivative would be x dot, y dot, z dot. That would be the derivative of rk. But it doesn't have to be like that. If, for example, rk is equal to cosine phi and 0, 0, then the derivative of rk would be minus sine phi times phi dot 0, 0. So what is the derivative of rk depends on parameters that we use to express rk. The k would still be the same point in all three examples, by the way. There would still be some point here. And it's just a point. It's just a point. So you need to be careful when you talk about derivative of a vector. It depends on the parameters that change in this time. Okay, good. Let's think about it. So let's just consider examples. So here, for example, we have vector rk described as a multiplication of the matrix, rotation matrix around z-axis. By the way, last lecture there were typos in the description of rotation matrices. A rotation matrix around x-axis was written as a rotation matrix around z-axis, and z-axis as x-axis. Hope I changed it in the GitHub, so hope this confusion is clear. Yep, was typos in mistakes in the lecture slides. All right. So here we have rotation matrix around z-axis. How we can tell it is around z-axis? Well, because z-axis remains the same. So which axis does not change when rotation is performed, that remains, that is the axis of rotation. So multiply, so find eigenvectors of this matrix. You would find the one of them is 0, 0, 1. Or alternatively, find multiplied by just 0, 0, 1, you will get 0, 0, 1. So it is eigenvector, doesn't change. Okay, good. So consider this scenario. What you get is this vector L1 cosine Q1, L1 sine Q1. So here what is changing is Q1, which appears under sine and cosine. Okay, good. Good. Now consider another example. We have Q1, Q2 plus rotation around x-axis. Notice this is how you get that the rotation is around x-axis. What doesn't change is the first element of the vector, which you multiply. And you get this expression, Q1, Q2 plus L1 cosine Q3, L1 sine Q3. So that's what you get. Here, what changing is Q1, Q2, Q3 under cosine, Q3 under sine. So those are parameters that are changing. Okay. We call it joint angles. However, in this case, this is not angles, this is translations. Clearly, they describe how point translates around x-axis and about y-axis, right? So x-axis this way, right, and y-axis this way. Okay, good. Good. Now, let's consider the derivative. So the derivative here is rather simple. What we can say is we can take derivative of this guy with respect to time, and it would be a chain rule. The chain rule tells us it is derivative of the expression for Rk with respect to the parameters q times the time derivative of q. Okay. So again, it is a chain rule. So we take derivative of r with respect to q, and then of q with respect to time. But q with respect to time is q dot. So we get times q dot. That's it. That's how we take derivative. If we didn't have parameters that change with respect to time, this whole thing would be 0. Okay. So this might sound obvious, but I promise you, even in people who spent years working in robotics, this leads to confusion sometimes. Just need to remember that when you take time derivative of a vector, this vector has to move for the time derivative to exist. If it is a constant vector, it doesn't move. It has no change in time, has no derivative then. What does it mean move? When we talk about a stationary point on a link, which is usually what we're talking about, like end effector position, center of mass of the second link, center of mass of the end effector, camera, point of camera, like some point in the center of the camera. All of those move as the mechanism moves. And mechanism moves only as joint coordinates change. So this would be the expression. How, like we take a chain rule, we express the coordinates of the vector partial derivative parameters, and then we take time derivatives of the parameters. That is how it's done. Okay. Now we can denote this partial derivative drk dq as jk, and we call it Jacobian matrix. The word Jacobian matrix is maybe familiar to you from calculus, and indeed it is the same Jacobian matrix as before. If you studied in a Russian environment, there is a chance that what you studied distinguished Jacobian matrix and Jacobian. Right. In Russian tradition, you call Jacobian matrix the matrix itself, while Jacobian is a determinant of the matrix. No one follows this tradition outside, and I don't think a lot of people follow it anymore in Russian. So just use the word Jacobian to describe Jacobian matrix. Determinant of a Jacobian is quite rare. You can find it still when you talk about KUKA robots and a few other things, but you know, not such a hot topic anymore. Determinant of a Jacobian matrix. Jacobian matrix doesn't have to be square most of the times. That's why, like most of the times, Jacobian matrix does not have to be square. All right. By the way, in our example, can someone tell me if Jacobian matrix here is for this guy would be square, or like what would be the shape of Jacobian matrix for this guy? Someone tell me.
Could you repeat the question?
What would be the shape of the Jacobian matrix for this guy, for Rk in this example? We consider that the vector of parameters here is q1.
1 by 1.
Come again?
1 by 1, dq1 over dt.
No, not by one, not 1 by 1.
I believe if we talk about Jacobian matrix, it should be 3 by 3.
Not 3 by 3 in this case, because we are talking about, again, our parameters here are just q1.
So the vector Q is actually a 1 by 1 Q1.
Yeah, the vector of Q is just Q1. So what is the Jacobian matrix then? Someone just tell me. I mean, we already said it is not 1 by 1, not 3 by 3. So what is it? Okay, the answer is 3 by 1. It has to be 3 by something, because if you take partial derivative of this vector, it would have to be to have 3 rows, right? Then yeah, 3 by 1, Ilya, thank you, in the chat. So it will have to have 3 rows. The number of columns is equal to the number of queues. So here, what is the size of the Jacobian matrix for this example downstairs?
3 by 3.
3 by 3, yes, because we have Q1, Q2, Q3. All right. Good. That is it. That's it. Good. Now, that's how it works. So for Jacobians, the more queues you have, the more it goes into like the fatter the matrix is. The more queues, the more columns. Okay. Now, here we have a description of what Jacobian is. Now, we can also define velocity as time derivative of Rk, as time derivative of Rk. Then what we have, if this is velocity, this is Jacobian, we have this description. Velocity of k is equal to Jacobian of k times q dot. That is extremely important thing. You can just memorize it, or you can understand it. In either case, this is extremely important. We say that velocity of a point on a robot is equal to Jacobian of this point times vector of generalized velocities. Okay, it's just how it works. Okay. Now, notice that velocity is linear with respect to generalized velocities or joint velocities. And the linear relation is given by Jacobian. That is going to be important for us later on.
Excuse me?
Yes.
So you said like analogy or another different meaning that this Jacobian matrix it transforms us from generalized velocities
Yes.
to I would say Cartesian velocities.
Cartesian velocities, yes.
So can we say that it's just transformation from some generalized coordinates into Cartesian?
Yeah, you can, if you want, you can say this is a map that maps space of generalized velocities to the space of Cartesian velocities with the point k. You can say it for sure, and it is good to ponder, like just think about it. What does it mean, etc. So it's a good thing to think about. Of course, you need to also keep in mind that this is just for this Jacobian here is just for the point k, and this is just velocity of the point k. So this is not a map of all Cartesian velocities to all joint velocities. It is just a map for velocities for the point k from generalized velocities. But you also can think about the fact that for any point on the robot, there would be such a map. So we can find a map for any point on the robot that would give us its Cartesian velocity from generalized velocities for the robot. So Q dot, generalized velocities, identify velocities of all points on the robot. And those maps are given by Jacobians. Jacobians themselves depend on Q, of course. So they will change as orientation of the robot changes. Like you can imagine drk dq depends on q, right? Okay. Now, one more thing to think about is additive structure. So consider RK. RK can be found as transition from origin of the world to O1, plus transition from O1 to O2, plus transition, etc., plus transition from some ON to K. So we can find position of K by saying, okay, we go from origin to O1, then from O1 to O2, then from O2 to O3, then from O3 to O4, then to O4 to K. So we can always find a position of K by adding a bunch of vectors together. So what is the Jacobian of K? Oh, Jacobian of K is partial derivative of K with respect to Q dot, or to Q, sorry. And that is partial derivative of vector here, O to O1, partial derivative of vector here, O1 to O2, partial derivative of vector here, or N to K, right? Because derivatives of a sum is a sum of a derivative. From that follows that Jacobian K is a sum of a Jacobians of individual vectors that form it. So if your vector is a sum of other vectors, and as we saw for all kinematic chains, this is exactly how vectors are. All vectors are sum of some other previous vectors. Then it means that your Jacobian would be sum of other partial Jacobians. So your Jacobian would have additive structure. That is not extremely important in itself. Although maybe you can say it is extremely important in itself. Basically, this leads to many algorithms which, instead of computing Jacobians this way, they compute them by computing simple Jacobians like this, and then finding the sums. And those simple Jacobians can often be computed analytically, as geometrically. So you can often find those Jacobians just by analyzing geometry of your links without actually taking derivatives. And all most fast algorithms that compute Jacobians and dynamics for robots, we'll get to dynamics later, but they do it this way. So they do it by analyzing geometry of the links. They don't actually compute derivatives. They just analyze geometry of the links. All right, so that is the last important consideration for Jacobians. Okay, so next, for the remainder of the lecture, we will discuss angular velocities. So I propose we take a short break, let's say 10 minutes, and in my clock, 11:57, we'll resume this lecture. And until then, this lecture will discuss angular velocities. That is extremely difficult topic, so please show up. Okay, I'll give you a 10-minute break. See you in 11:57. All right, I think we can resume. Okay. So we discussed before the topic of Jacobians, basically derivative of a position of a point. Is interesting. We saw a linear relation between velocity of a point and generalized velocities. Now, somehow we want to understand how to find derivative of a orientation, right? We know that points move and rotate, links move and rotate. Points do not rotate by themselves, by the way. But a link, a rigid body, like a microphone, can translate and can rotate, right? And if it rotates, it sounds quite good to understand its rotation in terms of kinematics. As in, like, what is the derivative of rotation? That happens to be most likely a single, how should I put it, not most confusing point, but kind of a quintessential difficult point of kinematics. So I don't know if there is anything in forward kinematics that is quite so Byzantine as derivative of rotation. So let us just look at it. We'll use all our tools that are built in the previous two lectures. Hope we'll understand it. Hope we'll understand it. The formulas that we'll get at the end are very simple, and you can look them up on the internet anytime. It's very easy. What is more difficult is to understand how we arrive at those formulas, especially how we arrive there with a complete understanding of basis, etc. All right, let's consider the problem. So we have a rigid body. Rigid body, notice, right? A rigid body rotating with angular velocity omega. Okay. There is a basis T attached to the rigid body. So this basis T is defined by matrix T, whom we know through its coordinates in the world frame. So we know T sub omega. Okay, T is just a three abstract vectors, but we know its coordinates as T in omega. Okay. Very importantly, it is stationary with respect to rigid body. So T sub omega is rotating the same way as a rigid body is rotating. Okay. What it means is that in terms of basis T, any point which remains stationary on the rigid body does not change its coordinates. So let us consider a vector R, which we know through its coordinates in T. So it would be R in T. Okay. So again, rigid body, you can imagine some sort of a thing. It has coordinate frame attached to it, right? And both things rotate together. If you have a point on this rigid body, in terms of this frame that attached to the rigid body, it is stationary. It does not change, because the rigid body is the frame of the rigid body rotates together with the rigid body. The point remains stationary on the rigid body. They rotate together. Coordinates of R and T remain constant. Okay. Good. Now, what is the velocity of the point K, who is defined by this vector R? Well, here we can remember what definition of angular velocity is. Definition of angular velocity is pretty much this. It is a vector that points somewhere in space. Its length is the angular velocity, as in how much rotation there is in a given unit of time, and its direction is the axis of rotation. And the same can be expressed this way. We can say angular velocity is such a vector that angular velocity cross product with r gives us velocity of the point r. Okay. Good. So as long as they are all in the same frame, this is true. This is just definition of angular velocity. By the way, here we all everywhere we will consider that the origin of the if you want to think about it in terms of frames, we would say the origin of the frame associated with the rigid body is at 0 and stationary. We don't need to think about any of this, but yeah. All right, so you can it somehow clearly implies from here. We say that there is no translation. The motion of r is described by pure rotation. Okay. Anyway, this is just definition of what angular velocity is. But we don't have to use this scary looking cross product. I don't know if any of you remember the formula for the cross product. Do you? You studied it not long ago, so maybe you remember, right? The formula for the cross product, how to multiply.
I mean, it, as in your slide shows, it is easier to compute cross product using skew symmetric matrix.
Yeah, but it's good to remember the formula. So maybe you can keep it in mind. But yeah, it is easy to compute this way. So instead of using the formula that you might have forgotten, I know that there is like two traditions. One is to memorize kind of like just memorize coordinate-wise multiplications, something like r, y, times omega z with a minus sign plus r z times omega y. That is the first line, the second line, third line, etc. Instead, you can represent it as a matrix vector multiplication, and this matrix will be called as you said, skew symmetric representation. So this matrix omega is a skew symmetric representation of this vector, and is denoted this way. So omega with this cross as a subscript with brackets. That is a very standard notation. Everyone uses it. So you can use this notation wholesale, as in just use this notation without change. Everyone would understand that you mean skew symmetric representation of a vector. And it goes like this. You have a matrix with zeros on the diagonals. Yeah, 0 here, here, and here. You have y coordinates here. Notice that it is skew symmetric. So if here is minus sign, here would have to be plus sign. Y coordinates here. Notice if here is a plus sign, here has to be minus sign. And minus x here. Here has to be plus x. Do I have to memorize it? No. Do I memorize it? No. You can look it up always. I think it is easy to memorize, so, but you don't have to. Okay, skew symmetric representation. So what we get is a formula where v is equal to some omega times r. Okay. Okay. Good. Now, next, let us just spend a little bit of time considering the frames in which we are working, oh, sorry, bases in which we are working. Well, this expression works as long as we're talking about vectors, not coordinates, right? Or if we're talking about coordinates, but in the same basis. So here is just vectors. We don't discuss coordinates at all. Here, vectors, but all in the world basis. So coordinates in the world basis. And here, coordinates in the basis T. All of this is legitimate. Because, wait, this just sounds like, vanilla definition, basic definition. This sounds like a reasonable extension of the original definition. This sounds bizarre. This sounds bizarre. And it sounds like you have to prove it. So, if any of you want, you can prove it. To prove it, you would have to consider how to go from here to here with matrices. But ultimately, all I'm trying to say is that we have three vectors which have the following relations. Right? Three vectors that have the following relations. Those vectors can be seen from this angle, can be seen from this angle. Still true, no matter from which angle you see them. So this has to be true as well. Doesn't matter in which coordinates you represent those vectors, the relations still have to hold. Okay. By the way, we can double check. Maybe I'm wrong. So right. You don't have to take everything that I say for granted. I invite you to double check this one. Okay. Good. Next. Let us note that sorry, I'm struggling a little bit with the annotation bar. I don't want to completely hide it away. Okay, so let us note that position of the point K can be given as this. We studied it before, right? What it is coordinates of R in T times T gives us coordinates of R. Or if you prefer coordinates only, then coordinates of R in T times T expressed in omega gives us R expressed in omega. Okay, good. So we have a position of R given this way. And we remember that time derivative of R in T is 0 because R is stationary in T. Okay, R is stationary in T. So position of R in T is 0. Change of position of R in T is 0. That means we can take a derivative of position of R to get V. This gives us expression ddt of T times R of T, which is just T dot times R in T. Okay. And we can do the same in coordinates. So velocity of the point K, so V can be expressed in basis omega. And this is how it's done. How do we arrive here? There are two ways. One is multiply this guy and this guy, who are equivalent, they're equal to each other, by omega transposed. And you get V omega here, R is a T dot omega here. Okay. Another way is to say, okay, we could have used this expression, and we would have gotten V omega here, T dot omega here, RT here. So there are two ways to arrive at the same conclusion. Now, remember that this is what we got from the previous slide. So what we have is this expression here, this expression here. Okay, notice I'm dragging around those frames because that's very important. Why is it very important? Well, what we're discussing this whole time is a rotating frame. So of course it is important in which frame we express ourselves. Like in the frame T, nothing rotates. In the frame omega, things rotate. So we have to be clear what we're doing. As long as we're talking about derivatives. If we talk about geometry, doesn't matter. If we talk about derivatives, one of the frames is rotating and others doesn't. So have to be careful. Velocities, on the other hand, still can be represented in both frames. That is not a problem. Velocities can be represented in both frames. So somehow there, you see, a radius vector represented in frame RT is stationary. Radius vector represented in R omega, not stationary. Velocity, however, of R is always there. Doesn't matter. Like it always has velocity, and this velocity we can represent very easily in the body frame. So can get convoluted. So it's very important to drag around all those notations very carefully. Okay, again, we have this expression and this expression. We notice that the right-hand side is the same, so is good. Is good. Now, let me just double check what did we do here. Yeah. So here in this last expression, instead of RV, so R omega, we can substitute this expression here. R omega equals to T omega times R tau, RT. So here is this expression. And overall, we get this whole thing. Okay. So velocity in the world frame is given as angular velocity in the world frame times T expressed in the world frame times R expressed in T. With that, we can equate the right-hand sides of both equations. So this is equivalent to this. So this is equivalent to this. Okay. Oh, sorry, not even that. We can equate right-hand sides of these equations. Sorry about that. We can equate right-hand sides of those equations, those two. So this guy is equivalent to this guy. And this guy is equivalent to this guy. So what is left is this guy here being equal to this guy here. Okay. They're all in the world frame. So if we can write it shortly like this. Omega times omega, so skew symmetric representation of the angular velocity, times the frame, so the basis of the this rotating basis, so times T, is equal to T dot. And alternatively, you can say that omega is equal to T dot times T transposed. So before we go to this last one, let me stress just how much sense it should make. This should make a lot of sense. So first of all, what do we say here? We say that the columns of T times rotation matrix, so it's times angular velocity matrix, gives us derivative of those columns. Well, of course, that is a definition of how rotations are performed, right? So each of those columns behave like a unit vector. This unit vector does not change its length, but it rotates. How does it rotate? Well, we know how any vector rotates in the angle in the frame which basis with angle velocity. We multiply skew-symmetric matrix omega with this vector. We get its derivative. So that's what we got. We multiply a column by omega. We get derivative of the column. That's how we get this formula. So formula 20 is just another way to restate the definition of angular velocity. Okay. And how did we get this formula? Well, we multiplied both sides by T transpose, and T transpose is identity. That's it. T transpose is identity because T is an orthonormal matrix, remember. That is the material of 2 lectures ago. So the fact that we can multiply by the orthonormal matrix on the left or on the right, and the fact that T goes away should be clear. Okay. Does it sound good, what we just discussed? Does it sound clear? You could, again, you could say that we looked at those 2 equations, and we get this equation by considering relations between them. Or you could say this equation is just a restatement of what angular velocity is. Angular velocity is what does it do to unit vectors? You multiply unit vectors by skew-symmetric representation of angular velocity, you get derivatives of those unit vectors. That's what we did here. This expression 20, can be represented in any frame. In any frame, as long as so this is about vectors, about pure vectors. You can represent it in the world frame. You can represent it in the body frame. Would still be true. Okay. Okay. If there are no questions, other questions, let me make the next step. So next, I want to show you just how much we can do with those vectors. So first of all, notice that this is a definition of orthonormal matrix. The fact that T transpose T is equal to I. That is pretty much the definition of orthonormality. It implies that columns are unit length and mutually orthogonal. So this is the definition, but we can take derivative of this definition, and we get T transpose T time derivative equal to 0, which means when we use a rule of derivative of a product, we get, remember, A times B, derivative is A dot times B plus A times B dot. That's what we get here. And we have 0 on the right, so we can shuffle this to the right, and we get this expression. So we get that T dot transposed T is equal to minus T transpose T dot, right? Just by differentiating here. All right, so now let's go back to our formula. Our formula was omega is equal to T dot T transpose. We can multiply it on the T by T on the right and get our formulas that we also discussed. Nice. 2 formulas that we have already seen. Now we can multiply it by T transpose on the left, and we get this formula. This formula here, you can easily represent it as omega in terms of some other basis. You can say it's omega T. You can say it is omega T is equal to T transpose T dot, where those coordinates are in the world frame, and this is somehow in the body frame. Because what you see here is a similarity transformation, a change of basis, it gives you a omega in a different basis, okay, different in a different orthonormal basis. Sounds great. We're not going to use it. I'm just showing you how you can achieve those formulas. Now, this guy is exactly the same as this guy. So you can get, if you want, you can get, replace it with this guy, but with a minus sign. That's what we do here. So again, we got a different formula. Now it is still omega somehow transposed in a different basis. Why do I say different basis? You have to be familiar with this, I think, from linear algebra. When you want to change basis in a matrix, you multiply it by inverse or transpose, depends on if the bases are orthonormal on one side and with the original on the other side. Like which direction depends on how you want to transform it. Okay. Okay. So we have this formula. Now, what we can do next is multiply it by t transpose on the left. Get rid of this t, and we get t transpose omega equals to minus t dot transposed. And we can multiply it by t, and we get omega is equal to minus t dot t transposed, which we could have gotten from here, I guess, somehow, using probably some discussion of this guy. But no matter. No matter. I mean, yeah. We got it somehow this way. Why did I show you all of this horror? When you're going to look up on Wikipedia or in cheat sheets, in the kinematic libraries, anywhere, when you're going to look up formulas for angular velocity, chances are you'll see one of those formulas. You can see there are many of them, right? I don't want you to have an impression that there is one that everyone knows. And if you don't see it, the writer is somehow dumb. No, in fact, there are a ton of formulas. And that is why it is so convoluted, right? Instead of trying to get one single clean expression, we can try to get 6 expressions. And here, notice, none of those formulas are even mentioned in which basis we are. We were in the world basis, if you want, or we were in the body basis, if you want. The key is that every matrix has to be expressed in the same basis. And as long as we're in the world basis, all of this makes sense, right? As long as we have omegas here, right? So I don't know if I can write it, but okay, let me just use arrows. If this is in the world basis, all of it makes sense. The expressions are clean. But imagine if we are in the T basis, then this is identity. T in the T basis is identity, of course. This is still something though. Omega is not identity. T dot is also not identity. It is equal to omega. So in the basis T, somehow we get that this becomes trivial. It becomes omega becomes equal to T dot. So this matters in which basis we treat it, but we can write it still in any basis. Instead of trying to memorize this or somehow keep this whole macaroni, kingdom of transformations in your head, just understand how we arrive there. I don't think in your career you would have to do it every day. I don't think you will have to do it every month or even every year. I think you just have to deal with software packages which already do it. And sometimes you would have confusion arising from the fact that your software package represents you with a strange formula. Sometimes you would see, let's say something like this, and you'll be like, what is it? How did we get here? And then you can go through derivations, which is not very difficult. And you can verify that the formula is indeed okay. Sometimes your software package will write you something like this. I would say, okay, this is omega. I will use, I mean, how do I write omega in Latin script? I cannot, right? I'll just say U to increase confusion. And I would say, okay, this is UAB. UAB is your angular velocity skew symmetric matrix. It implies that it is angular velocity from frame A to frame B. What did writer mean? I don't know. In which frame it is expressed? I don't know. UAB. Then I would say, okay, times A, frame A, equal to, let's say, dot A. Looking at this, trying to understand what's going on, I think might be futile. I mean, you would have to read through documentations of what the writer wanted to say, because his notation AB is just as random as my notation through my lectures. It would have been nice if we had a unified notation throughout the whole robotics, but I don't think we do. I don't think we do. Even if we do, programmer who is making documentation for his new software package might not be aware of it. So relying on the conventions here is, I think, dangerous. Instead, you can look at this notation and say, okay, what they're trying to say is that his angular velocity times some sort of a frame is equal to derivative of some sort of a frame. This looks a whole lot like this formula here. Let's verify that in the rest of his documentation, UAB indeed refers to the angular velocity expressed in, let's say, world frame. A refers to the local body frame. If this is all true, then great. We understood what the writer was trying to say. Maybe it doesn't end this happily. Maybe you have more steps to take. But important is you try to understand what's going on through derivations. You don't rely on trying to read subscripts. You just derive, and then you try to understand. Humans are very imaginative when it comes to notation. So, you know, I could show you a notation of one of the very good software packages that we use. And until I derived this for this class, I didn't even want to try to understand some of their like indices. It was difficult, but I double checked those formulas against the indices. It made sense. Just saying. Somehow this derivation makes it clear. Okay. I hope you got my point. Oh, by the way, my annotations somehow were on top of the chat. Yeah, but no one wrote anything. Good. Now, last point to make. We have relations between omega, big omega and small omega. Big omega is this guy, small omega is this guy. We can write down this skew to vec function that somehow takes this matrix and gives us this vector. Notice this is not a function that you can write as a matrix vector multiplication. If you can show me, it is a linear relations, of course, but I don't think you can write it as a multiply this by vector, multiply this by matrix, etc. There are a few operations like this, like skew, vector to skew symmetric is one of those operations. Vectorization is one of those operations. Reshape, I think, is one of those operations, etc. So operations which are very easy, shuffling, slicing, etc. But difficult to express in terms of vectors and matrix multiplications. So those operations are linear. Like this is still a linear operation. here, right? This is a linear operation, but it is not easy to represent it in terms of a vector matrix. It should be possible. It's just not easy. Okay. Now, since this guy is linear with respect to t dot, omega is also linear with respect to t dot, because this operation is linear. And t dot is obviously linear with respect to q dot. Why? Well, what is t dot? T dot is dt dq times q dot. You just use your favorite, what do you call it? Chain rule. Just use your chain rule. Okay. All right. Okay. So what we get is that omega is linear with respect to q dot. Now, this means we can take a Jacobian, and it would have this linear structure. So consider omega, function of q dot. We can take a Jacobian. Oh, sorry, here's a mistake. Here's an error. Let me. This is not q dot. This is just q. Okay, so we can take a partial derivative with respect to q. Oh no, wait a second. That wasn't an error. That was correct. Sorry about that. So we can take a derivative with respect to q dot here, and you can multiply it back by q dot, and you would get this Jacobian representation, and would actually be correct. Okay, since omega is linear with respect to q dot, you can take derivative of omega with respect to q dot, and you would get like a linear map that basically maps q dots to omegas for this particular rigid body. So what will happen is you'll get this Jacobian Q. So this Jacobian is you find it by taking derivative of omega with respect to q dot. All right. And when you take a derivative of omega with respect to q dot, the Jacobian is not going to be dependent on q dot because omega is linear in q dot. All right. So now we have translational Jacobian that relates linear velocities to joint velocities. And we have rotational Jacobian, which relates angular velocities and generalized or joint velocities, right? So we have those two things. Remember that to define translational Jacobian, you need to define a link and the point on the link whose Jacobian we work with. To define a rotational Jacobian, we need to only identify a link. Okay. Only identify a link. Good. Yeah, and here we have a mistake. Here we have a mistake. So let me fix it. Here is a dot. Here is a dot. Let me make sure we don't have any errors anymore. No, here we don't have mistakes. So for some reason, I'm paranoid about this. No, the slides so far don't have mistakes. It's just me being paranoid. All right. So finally, let's discuss how Jacobians relate to frame transformations. How Jacobians relate to frame transformations. So we could take a Jacobian of R, vector R, with respect to Q. Okay. And It will be G of Q. Okay, familiar stuff. If R was in world frame, the Jacobian would also be in the world frame. In which sense? Well, what is Jacobian? Jacobian is a matrix whose rows are partial derivatives of coordinates of R with respect to Q. But those coordinates of R are, as I said, coordinates, right? So they are taken with respect to some sort of a basis. And what you would have here is rows would depend on which basis R was represented to in the first place. So indeed, this R in omega is a coordinate representation of a vector, and this Jacobian is a matrix of partial derivatives of those coordinates, that is the rows, and with respect to various Qs, those are columns. Okay. Now, let's say we want to, we have a basis T expressed by matrix T in omega. And T is constant. Okay, so of course we can do it, right? We have coordinates in the world. We can multiply it by T transpose and we get coordinates in T. Again, remember second lecture, right? Now, again, of course, we can take a derivative of this new vector, T R in T. And what we get is, you know, dr dq, right? But this would be the same as the same as T in omega transposed times Jacobian, original Jacobian, so Jacobian in the world frame. So this guy is this guy. Why is this so? Well, because look at this definition. If here we, instead of R, we put this whole guy. Sorry, let us go the other way around. So we're going to take a derivative of this guy, right? We know that partial derivative of this guy is 0. Like we're going like step by step. We want to identify where we have what kind of derivatives we have. This is a product of two entities. One of them is constant, right? One of them is constant. If it is constant, then it doesn't have a derivative. So we treat it as a constant. We take it out of the brackets. Next, we have to take a derivative of this guy. But derivative of this guy is already known. Here, it is equal to Jacobian. So this is how we get to this formula. This is a constant, this is a Jacobian. Okay. So we see that there is a relation between two Jacobians. Jacobian is a world frame. We wanted to transpose it to Jacobian in T frame. We multiply it by T transpose. Alternatively, we knew Jacobian in the T frame. We multiply it by T. We get Jacobian in the world frame. We can play the same way with velocities. So Jacobians depends on the coordinates in which the vectors which you differentiate were expressed. And it is always important to think about it, in which coordinates your Jacobians are. I think we have a tendency, I personally have had this tendency previously, to hope that Jacobians are expressed in the correct frame and continue on. Is a source of errors. Don't do this. Don't hope that Jacobians are expressed in the frame in which you think they are. Check. And the plus side is that if you checked your vectors and you know in which frames they are expressed, your Jacobians will always be expressed in the correct frames, because Jacobians inherit their frames from their parents, so from their vectors. Downside is that if you work primarily with Jacobians, not with vectors, so for example, if you do geometric methods, you derive them geometrically, not as derivatives, there is a chance that you will mess up. So double check. Right, I think that should be it for today's content. Yep, that is it. Do you have any questions? All right, if not,
Can we expect some of this type of tasks in like midterm, for example, when we have to compute by hand some Jacobian for, let's say, specific angles?
yes, you can. It wouldn't be very difficult, but you can expect it on midterm for sure. You can expect it on midterm for sure. Any other questions? All right. Thank you for finding time, and we'll see each other next time. Next time we'll discuss fundamental subspaces of Jacobians, preparing to study inverse kinematics. All right. See you then.